Okay, ladies and gentlemen, this is a solution. Which one of these is the solute? Green Skittles. Why did you assume that?
There's less of that.
There's less of them. And so this would be the solvent. In order for this solution to form, you have to do three things. The first thing you have to do is expand the solute. And that's actually to push the pieces apart so there's room between them. Guess what the next step is?
Fill in the gaps with the salt.
Well, before I can do that, what do I have to do? Expand the solvent. What does that mean?
Spread it out.
Spread it out. So now I'm spreading out the solvent. All right. And then we have the solute and the solvent interacting. And no, they don't mix together. This is what it would look like if you shrunky dunk yourself down. Thank you. Yeah, they do. The solute is surrounded by the solvent. And on this level, this is what a solution would look like.
So it doesn't really dissolve, it's just
Well, it doesn't really dissolve, it's actually
surrounded.
surrounded. Now, here's something three things I would like to point out to you. First of all, would you think expanding the solute is endothermic or exothermic?
Endothermic.
Endothermic. You saw me do some work on it, didn't you? Was expanding the solvent endothermic or exothermic?
Endothermic.
It's also endothermic. The process of forming the solution where the solute is surrounded by the solvent can be exothermic or endothermic, depending on what the solute is. Okay, so far so good. What was the third thing I wanted to say about this that I can't even remember? Because I'm so fixated on I really like marshmallows. No, it didn't have anything to do with that. Oh, that's all I really want to talk about for right now. Okay, now let's look at your notes, which you will notice say pretty much the same thing. Here, I have some that I printed with a color printer. All right. So when we're talking, oh, I know what it is. Tell me the two type of changes that you're familiar with. Chemical and physical changes. All right. What are the hallmarks of a chemical change?
New substance form.
A new substance is formed. Is energy required?
Yes.
Yes. Lots or little?
Lots.
Kind of a lot. So, and you know, in relative terms, a lot. Now, in a physical change, tell me what happens.
Changes shape.
If you change shape or something like that, you don't change.
Element.
Or makeup.
Right. Yeah, I remember in your middle school, you always said, oh, you can go back with a physical change. You can always make it go back to what it was. And it takes just a little bit of energy. Now, in the middle, we have something called an ambiguous change. I know. Solvation is an ambiguous change. Because really, when you looked at those little pictures that I made, you can't, something's changed, hasn't it? You made the little flower with the, you know, the middle was the green Skittle, and then the marshmallows around it. That's something different. So solvation is an ambiguous change. Okay, so here we go. The act of dissolving takes into account the enthalpy, the change in during a reaction, and the disorder of the solution. Now, for most of the time, the entropy increases. Certainly, anytime you have a solid solute in a liquid solvent, there is a increase in entropy when the solid is dissolved. Okay. So step one, expanding the solute is endothermic. Step two, expanding the solvent is exothermic. Step 3, when they form the solution, can be endothermic or exothermic. Now, you know not all things dissolve, correct? Uh-huh. It depends on the entropy and the enthalpy. All right. These things favor solution being formed. If in my solute I have very weak intermolecular forces holding them apart, there's just a little bit of energy needed to expand it, that gives room for the solvent to get in there. If my solvent particles don't like each other very much either, weak intermolecular forces, that favors solubility because that frees them up to surround the solute. And if the intermolecular forces between the solute and the solvent are attractive, if they like each other, that favors solution as well. So far, so good? Okay. That brings us to one of the overriding principles in solution formation, and that is like dissolves like. What does that mean? Anybody? Anywhere? Like dissolves like. Yes. Those substances with like intermolecular forces, really quick, the type of intermolecular forces are London dispersion,
Hydrogen bonding.
and
Dipole.
dipole. So if you have two nonpolar solute and solvent that both just have London dispersion forces, chances are they will dissolve. Why? Weak solute attractions, weak solvent attractions. Now, if you had a polar solvent, let's say, I don't know, water, and a nonpolar solute, let's say wax, they would not have a very strong attraction for each other, so they would not favor solubility. Over the winter break, I spent 9 bazillion years watching TV because I had nothing better to do. I was snowed in and I was stuck visiting relatives. And so I saw a commercial for a product that was an ear wax vacuum.
I've seen that, the wax bag.
What is it called?
The wax bag.
The wax vac. And it showed some guy jamming Q-tips in his ear and he yelling, hey, yes, right, like he went through the other side of his head, right? Or people pouring water into their ear. And did that work?
No, of course not.
Why
It's
didn't it
not
work?
soluble.
Why
They're
isn't
not-
it soluble?
Attractive.
That's exactly true. Water is polar and wax is non-polar. Now, if you wanted to dissolve earwax, don't try this at home. I'm not giving you medical advice right this moment. If you wanted to dissolve your earwax, what would you put in your ear?
Hydrochloric acid.
Why do you people do that?
It's strong.
It is hydrochloric acid is a strong acid that ionizes.
Vinegar?
Precisely.
Precisely, not vinegar either, it's also an
So if
acid.
it's not polar but ionized,
It's a solution of, it totally breaks apart into ions.
Or you could just get a wax vac.
No! You know what? I would call your mother and say, he really wants a wax back for next
Wait, what do you use?
Okay. Baby oil.
Wait, what do you use?
Baby oil. That makes
That feels
sense,
so
doesn't
Wait,
it?
why was she?
Yeah.
Why in the commercial were they sticking a candle in her ear?
There's a theory.
Okay, because people who are not very intelligent, I think she was trying to melt the wax.
Oh, that works.
Yeah.
Don't do that! Don't do that.
There's some
Yeah, it doesn't
saying
work. People
Maybe she's trying to put wax in there.
They put like a candle there and light.
Okay, you could, you would have, okay, if the air outside your ear was hotter than the air.
Yeah, they just dip it and dissolve it.
Don't do any of that. But go to the doctor and follow your doctor's
That's what they
orders.
told me to do.
Okay, now we're
That's
back
really
to this. Now, let's talk about, you do realize that you could have any phase of matter as a solute and any phase of matter as a solvent, right?
Sure.
Okay, here is, I will give you the solution, you tell me the phase of matter. Shaving cream. What is the solvent? What is the solvent in shaving cream?
Water.
Air.
Air. And then what is the solute?
The stuff inside the can.
The cream.
The cream. Okay, there we go. Here we go. Brass.
So,
Copper.
I can't never remember. Oh, here we go, because this one I know. 14 karat gold.
Gold.
Gold is the,
Solvent.
solute.
Solvent.
and here, don't step in front of the camera, because then I have to get your permission to be in the camera. He's not here. Okay.
Quick, put your head in front of the camera.
You're not putting the camera. Okay. Alrighty. No, you can't. No, you can't. No, you can't.
I'll do it.
I
I'll
forgot
do
what we were
it.
talking about. Okay, do not, you know what? Throw your sorry self out. You'd be in trouble. Okay, so now we've talked about you can have any state of matter. I want to talk to you specifically about gas solutes. Got that in your brain? Gas solutes. A gas solute in a liquid particularly. I can think of two solutions where the solute is gas and the solvent is a liquid.
Soda.
Number one is soda. So CO2 is the solute dissolved in the syrup, which is the solvent. The other one that I'm thinking about is oxygen, which is the solute dissolved in like ocean water or pond water, right? So fish rely on the dissolved oxygen in a pond or the ocean in order to live. Now, in order to get the most amount of gas dissolved in the liquid, you have to do two things. Number one is you have to depress the solution temperature, get it? The low temperature, high dissolved gas. Anybody aware of the dead zone in the Gulf of Mexico in the summer?
Yes.
Okay, there is a spot in the Gulf of Mexico where the temperature of the water gets so high that the dissolved gases become so rare, right? Most of them are undissolved and out above the water that aquatic life can't live. So literally, if you were a fisherman and you decided to go fish in the dead zone in the summer, what would you catch?
Nothing.
Nada, because there's nothing there. The aquatic life aren't dumb, they're leaving. Now, the winter comes and the temperature of the water drops and more oxygen becomes dissolved and the fish can live there. Another example of that is, I don't know if you've ever chugged a Coke?
That sounds like
That's a
that.
It hurts your
mistake.
throat, and what's the, if you take a Coke out of the refrigerator, you pop the top and you drink it down, what happens? Don't lie to me, what happens? You burp immediately. Why?
It's carbonation.
Because there was a lot of carbonation in that soda that you just drank down and your stomach's like, no moss, it's coming out. One of the remedies for a stomach ache is to take Coke, heat it up, and then drink it. Because there's no carbonation in
So you
it.
can
And it
just
actually
pick it up and
says,
get rid of the carbonation.
right, you do that, okay. Now, I think we have talked enough that if you want a gas to dissolve in liquid, what should you do to the temperature?
Heated.
Cool it. Okay, if you want a gas to dissolve in a liquid, the other thing you could do is manipulate the pressure. If you actually force the gas into the liquid, more will dissolve, yeah? You're pushing it in there, which is how they bottle Coke.
Wouldn't that
As well.
raise the temperature?
Huh?
Wouldn't that raise the temperature?
No, they're very
You-
tricky.
if you let
Is
it-
that why
But that-
when you
that's-
shake it, the pressure increases and you open it, that's why it opens up?
Yes, exactly. Okay, so that's what you need to know about that. Now, I think in your daily life, you have tried to dissolve enough solid solutes so that you know what to do to increase the solubility. Name me one thing.
Increase temperature.
Heat it up. Heat it up. A solid dissolves more readily in a hot solution. One more thing.
Increase surface area.
Increase the surface area, which would dissolve faster, a cube of sugar or a pack of sugar.
Depends which
or
one's
granules.
hotter.
Pack, well, if you empty the pack.
Pack. Temperature being the same, holding the constant, so holding the variable's constant, yep, the granulated sugar would dissolve. And then, one more thing. I think you said it.
Stir it.
Stir it up, stir it up. All right, almost done. I would like to draw your attention to the solubility graph. Without being labeled, you should be able to identify the state of matter of the solute because of the shape of the graph.
Yes.
And it is a gas. As the temperature is increasing, the solubility is decreasing. And that is the trend. Okay? That's notes for today.